Today, we are going to talk about linear block codes. In digital communications, channel coding is one of the criteria in the digital transmission where the error correcting codes, error control and correcting the codes which are very essential, the channel coding. So we know very well that earlier the source coding we discussed. Now this is now the channel coding under which whenever the digital transmission through a channel we undergone that we perform the data which is transmitted in the channel, the digital communication. So whether the transmitter is going to transmit and the data which is received at the receiver or the other side, whether it is that data is receiving correctly or not, we can check that data. If there is an error or there are some errors in that received data, we can identify those errors and we correct those errors. And so that whatever the transmitted signal or data which is retrieved back. So those for which the channel coding, the different coding techniques are required. So there are linear block codes, cyclic codes, and convolutional codes. So here we discuss linear block codes in this session. So this linear block codes is block by block. This is block codes. These are all come under block codes. So we transmit the message bits here in the digital transmission. There are k number of message bits, and we transmit these message bits in a channel as a n-bit code word. This is n-bit code word by adding some parity bits. So how many parity bits that are added? N minus k. N minus k bits are added to the k number of message bits. So this is one of the code word as a block code. So to generate this linear block code, the property of any code here, the sum of two code words, if at all added in modulo 2 additions, that will produce another code word that is also a linear, that is called a linear property. So any two code words added and which generates another code word is a block code. So this is we represent n comma k linear block code with n number of bits of a code word of a k number of bits message bits and n minus k parity bits. So in this linear block code, M0, M1, M2, M3, Mk minus 1 are the message bits. There are k message bits. Okay. So we add B0, B1, B2, Bn, n minus k minus 1 parity bits, n minus k parity bits. So this total whole code word is a code word. Okay. There are different code words like 2 power k distinct message bits, message words like for k number of bits, If at all there are 4-bit code, 4-bit message word, there are 2 power k, 2 power 4, 16 message blocks. So we can generate 16 code words like that. So this is the structure of the block code, which we represent as code word C0, C1, C2, Cn minus 1. This is n-bit code word. In this code word, there are B0, B1, B2, Bn minus k minus 1, n minus k parity bits, and M0, M1, M2, Mk minus 1, k number of message bits. This is the block of code word. So we represent message bits and parity bits M and B separately here for the understanding. And these message bits may be either side, parity bits can be added either side. What are the parity bits? The n minus k parity bits are linear sum of the k message bits. So this is the linear sum of the message bits. There are k message bits m0, m1, m2, mk minus 1 with their coefficients p0, p1, p2, pk minus 1 of every ith bit of parity. So this is where the coefficients, that those p are the parity coefficients. Okay, for every ith bit of the parity, so there are the parity coefficients. Okay, that is j pij equal to 1 if bi depends on mj. So that is we represent, if it depends, that can be noted as 1, otherwise it is 0. So the parity matrix, here the parity coefficient matrix n minus k, that is what the parity bits, the coefficients are the pk minus 1. There are pk minus 1 by n minus k minus 1, the order of the parity coefficients. So this is one, each row p0, p00, p01, etc. p0 n minus k minus 1 is the parity coefficients, and similarly, see, this is p10, p11, etc. So pk minus 1 0, pk minus 1 1, pk minus 1, and minus k minus 1. See, these are the coefficients of 1 or 0 can be denoted with the linear sum of all the message bits as a parity bit. We represent in the matrix form, as we said that message bits as M and parity bits B in the code word matrix form B and M, and this B is the parity coefficients, the linear sum of the parity coefficients of M and P, as B equal to M and P. So this message bit M. So this code word is nothing but M multiplied with the parity coefficient. This is where the M multiplied with P and I, unit matrix. So here this parity coefficient matrix K by N minus K order, and unit matrix K by K matrix. This message bit, the message K bit message, so this K by K matrix, and this parity coefficients of N minus K, bits for K by N minus K parity coefficients. So this is what the code word generated by multiplying the message bits with this matrix. So this is called a generator matrix, denoted the generator matrix P and I of K by N size, K by N matrix. So this C equal to M into G. We multiply the message bit sequence as a block with the generator matrix. We can get the code word, linear block code. If this code word is transmitted, the receiver is received that code word. The received word is R, for example. So the transmitted code word is C. So whether we need to check that the received code word R equal to C, whether R equal to C or not. So to check this parity check matrix is required. To check this error, the parity check matrix is required H. This is called denoted with H. The relation between H and G, what is the parity check matrix we choose? The relation between the parity check and generator matrix is GH transpose equal to 0. So this is the relation, so that we generate a null, so that the relation between G and H transpose. So then as G equal to, as you know that G equal to P and I matrix, okay, and this G and H transpose becomes 0. So then H should be I and P transpose. So this I and P transpose, then GH transpose becomes, this is a G, P and K matrix, and H transpose is transposing this H, I and P. So this multiplication P into I, P and I into P, P plus P, this modulo addition becomes 0. That is null. So which is nothing but GH transpose equal to 0 null condition. CH transpose, if at all you verify CH transpose code word into H transpose parity check matrix transpose, CH transpose, this C is M and G and H transpose. This is equal to 0. That is nothing but this is GH transpose equal to 0. To verify this CH transpose, we choose GH transpose as a null, as a 0. Now we know the generator matrix and the parity check matrix for the generation of the code word, for the checking the error in the receiver with parity check matrix. So this is a received word. If at all the code word is not equal to received word, having some error. So that error C plus C, that is the received word. There is an error pattern, E is called error pattern. What is that error pattern? Here, see, ith element of the E equals 0, then that corresponding element of R is same as C. That is a code word equal to received word, and that particular ith pattern of error is 0, then both are same. If error pattern is having ith element is 1, then there is an error in that R received word, then R not equal to C. So error pattern EI, that ith bit is 1, then there is an error of ith bit. If error is 0, then ith bit, that error, that code word is same as the received word. So we need to check whether the syndrome is generated or not. What is that syndrome? So if there is an error, the syndrome is generated with the parity check matrix. While checking with the parity check matrix, the received code word is generated as a syndrome. So that syndrome is RH transpose we calculate. If syndrome is generated, there is an error. So this is what syndrome S equal to RH transpose. So R is nothing but a code word plus error pattern, C plus C and H transpose. And this is CH transpose plus EH transpose. This is 0 anyway. CH transpose we have seen now condition, then syndrome equal to EH transpose. So if there is an error, syndrome is generated. So if there is no error, syndrome is 0. So that is what the syndrome depends only upon error pattern. If there is no error, the syndrome is 0. That is null. If there is an error, syndrome is not null. Okay. This is what the linear block code syndrome S is equal to the sum of the rows of the transmitted transposed parity check matrix H transpose with the errors. Okay. So this is where how many errors that can be detected and corrected based on the Hamming distance. Based on the Hamming distance. What is the Hamming distance? Okay, the number of ones in a block code is called number of ones in a code word is called Hamming weight. That is Hamming distance. If smallest number of ones in the Hamming in the code word, that is the minimum distance. If any code word having a number of ones out of for 4-bit message word, 16 code words are generated. Out of those 16 code words, minimum number of ones whichever code word is there, that is the minimum Hamming distance, D minimum. So based on that D minimum, error correcting capability is it depends. Okay, so there are t number of errors that can be corrected where d minimum must be greater than or equal to 2t plus 1. The t number of errors can be detected. So that t, how many bits that can be corrected? T must be less than or equal to half minimum aiming distance minus 1. If minimum aiming distance is the d minimum is if three ones are there in any code word, so that is 3 minimum. So d minus 3 minus 1, that is 2 by 2, that is 1 bit. So in that code word, only 1 bit can be corrected. As an example, if at all we see the example here, 7, 4 code word is generated. That is what n equal to 7 and m equal to 4. That is what n comma k. Okay. So n minus k is 3 parity bits. These are the parity bits, message bits, and code word length. So as we know that generator matrix P and I, this is k by n minus k and k by k matrix of k by n generator matrix. The parity coefficients to generate the parity bits P, the coefficients Pij can be taken 1 or 0 based on the linear sum of those message bits. So if at all we choose the parity coefficients here, B0, 1, the linear sum of these coefficients of M0, M1, M2, M3 like 1, 0, 1, 1. So this is what parity coefficients, ith bit, and B1, the parity coefficients, parity bit coefficients 1, 1, 1, 0, and similarly B2, this is B0, B1, B2. So B0, 1, 1, 1, like this is what P matrix, okay, k by n minus k. So 4 by 3, and this is k by k, 4 by 4, unity matrix. This is unity matrix. So we can generate parity check matrix also, because H is I and P transpose. As we said that GH transpose must be null. So then H becomes I and P transpose. So whatever the P here, whatever the P here, the P parity coefficient matrix transpose of that, and this I matrix is unity matrix. So this here n minus k by n minus k. So this is 3 by 3 unity matrix, and n minus k by k. This is 3 by 4 P transpose matrix. So you transpose this matrix 1, 0, 1, 1, 1, 0, 1, 1. So 1, 1, 1, 0. So 1, 1, 1, 0. So 0, 1, 1, 1, 0, 1, 1, 1. This is the P transpose matrix. So here, example is message bits are taken 1, 0, 1, 1. Message bits are taken 1, 0, 1, 1. So generator matrix is taken as before like this, and we can generate a code word by multiplying with the generator matrix. There are 2 power 4, 16 message bits will be available. So as an example, we have taken 1011 out of 16 message bits message block. So this is what one see here 1, 0, 1, 1 multiply and m into g. This is m and into g, m into g. That you will get multiply, you will get the code word. So this is where one, see here, multiply this m into g, you will get here see here, 1 into 1, 0 into 0, 1 into 1, 1 into 1. That means this first row, third, second and third rows can be added. So this 1, 1, 1, 1. So 1, 1, 0, 0, 1, 1, 0. So this one is 1, this 0, this is 1, this is 1. So 1, 0, 1. So this is message bits. This is message bits. This is parity bits B. So this is parity bits. So see, code word is parity bits and message bits. So 1011 is the message bit, as this we get because it is a unit matrix is multiplied here. So this is the code word. The received code word is R, may be same or may not be same. If see third bit error, for example, it is there, third bit error is considered. So we need to find out the syndrome from the RH transpose. We need H and then H transpose. Write down from the generator matrix. H is the parity check matrix. This is the parity check matrix. And I and P transpose is the parity check matrix. You generate I unit matrix 3 by 3. Parity check, parity coefficients P transpose is, this is you transpose this P and this you get, and multiply this code word and this H transpose. H transpose, you transpose this matrix as this matrix H transpose, you transpose this 1 0 0 0 1 0 like this 0 0 1. So this is transpose matrix. So R received code word into H transpose. For example, 1 0 1 1 0 1 1. So you multiply RH transpose. So this one and this one and this one is also okay. This one and this one multiply. They add this. Okay, add this. So 1 0 1 0 1 plus 1 0. So this is 0. Similarly, 0 0 0 1 plus 1 0. That is also 0. Yeah, here 0 0 plus 1 1 1 plus 0 1 1 plus 1 0 0 plus 1 1. So this is the syndrome 0 0 1, not null. So there is an error. What is the error pattern? Error pattern, the syndrome depends on error pattern. So EH transpose. So whatever the error pattern we multiply with this H transpose, we get the same syndrome. See, if at all there is an error pattern of like this, H transpose, that particular row having syndrome 0 0 1. So that means third bit is the error. So 0 0 1 0 0 0 0 is error pattern. We get the same syndrome of like this 0 0 1. So then we add this error pattern to the received code word R plus E. So this 1 plus 1 becomes 0. So we get the code word which is transmitted after correcting this error. We get 1 0 0 1 0 1 1. This is what the received code word, which is same as the transmitted code word. So through finding the syndrome value, if it is not null, find the particular row of that H transpose, which is equal to the error pattern of that particular bit. So add that error pattern to the received word. We will get the code word as it is exactly. So this is what the linear block code, how to transmit the data and how to correct the data through syndrome calculation. So using generator matrix, we generate the code word. Through parity check matrix, we check the syndrome, the error, and finding the error pattern, add that error pattern to the received word, we'll get back the transmitted code word. So that is what linear block code. Thank you.